Welcome to the class. Today we are going to see nitration of benzene. Nitration of benzene is an example of electrophilic aromatic substitution reaction. Let us have a short rewind of what is electrophilic aromatic substitution reaction and then we will come to nitration of benzene. Electrophilic aromatic substitution reaction. For that we have to see the structure of benzene. Dear students, the structure of benzene has 3 double bonds. That means it has 6 pi electrons. The 6 pi electrons of benzene are in constant dynamic motion. They are in constant dynamic motion. So this results in 2 structures of benzene. The 2 structures, the combination of these 2 structures is the resonance hybrid structure of benzene. Why we are calling the delocalization of electron is referred to as resonance. So because these structures arise from the delocalization of electrons, the structure that results from the combination of these 2 structures is the delocalized hybrid, that is a resonance hybrid structure of the benzene ring. Now if I introduce an E plus into the system, do you think it will be able to catch an electron pair? Never, because the electrons are in dynamic motion. So you can say that delocalization or resonance actually has made the benzene ring very unreactive. It has made the benzene ring very stable, and such stabilization is referred to as the resonance stabilization. What option then has electrophile has? It has another option. It can replace one of the hydrogens among these benzene ring. The carbon, each carbon has one hydrogen. It can replace any of the hydrogen and it can come and fix here. While the hydrogen, it can go with the base. So this benzene, it undergoes electrophilic aromatic substitution reaction. Let us now come to nitration of benzene and understand it much better. For that, I will write the reaction first and then the mechanism. Let me write the reaction first of all. The benzene ring reacts with nitric acid in presence of H2SO4 to form nitrobenzene. You can attach the NO2 group anywhere you like, and HSO4 minus and H2O. So this is the reaction. It reacts with HNO3 in the presence of H2SO4 to give nitrobenzene plus HSO4 minus plus H2O. Let us now see the mechanism of action of how this reaction proceeds. For this, the step 1, it is made up of 3 steps, as it is electrophilic aromatic substitution reaction. It is made up of 3 steps. Step 1 is, do you remember who is the problem maker here? Yes, you are right. It is the electrophile. And who is the electrophile here? Yes, NO2 plus. So electrophile has to take birth, right, to create the problem. So that is what we are going to see here. The formation of electrophile. Formation of electrophile. Let's see how it is formed. HNO3 reacts with H2SO4 to form NO2 plus HSO4 minus plus H2O. So here we go. This is the electrophile that is formed, and this is the base of this acid. This is the conjugate base of this acid. Okay, and H2O is also formed. Okay, so to know how NO2 plus is formed, you can rewrite this structure like this. Right, so oxygen has a lone pair of electron, and when it reacts with H2SO4, H2SO4 actually releases H plus, right? So this H plus comes and joins here. So what we get is HOH, we get N, O minus. So because now O is protonated, and because O has lost its lone pair of electron, it becomes positive, right? To negate this positive sign, this electron pair shifts here. So now we get H2O, but when it shifts here, this nitrogen becomes positive, so we get N plus, right? And N plus O2. So that's how NO2 is formed here. Okay, I hope you understood. That is a formation. This is only the step 1, the formation of electrophil. So the villain has taken birth. Now the villain would act at the benzene ring. So second step is the formation of a carbocation, and it results because on attack on the benzene ring, right? So the E plus that is born now, it is not going to sit idle. It will surely attack the benzene ring and form a carbocation. Let's see, formation of carbocation, step 2, formation of carbocation. Okay, let's see. The electrophil NO2 plus it will surely attack the benzene ring. Okay, now suppose it takes this electron pair, then what would be the structure? You guessed it right. The electron pair, if it is taken here, if the NO2 plus takes the electron pair here, NO2 comes here. Each carbon has each hydrogen, one hydrogen. I am showing the hydrogen for this carbon atom, not showing for others. For this I am showing so that we can better understand the mechanism. I am showing it for here. So when this electron pair was shifted here, okay, this electron is actually, pair is made up of 2 electrons. When this was given here, the loss was for this carbon, right? This carbon didn't have any loss, its electron is here. It just gave this electron to NO2. So loss is at this carbon atom. So you write it like this. Fine. Now to negate this positive charge, this pair comes here and you get the second structure, which is like this. You write NO2H and the positive sign comes here, because when this shifted here, this carbon didn't have any loss, its electron is here only, but the electron that was here, it got shifted here, so this carbon had loss, so therefore the positive charge now rests on this carbon atom. Now this electron pair, to negate this, it is shifted here and we get a third structure. You can write NO2H. Now we get this structure, right? So as you can see earlier, this carbon has a loss, okay, this carbon doesn't, so the positive charge now rests on this. So you can represent the overall structure. These 3 structures you can represent it as a single structure here, here NO2, here H, and you can write like this, and positive sign is just rotating around whole of the benzene nucleus, right? First it was here, then here, and then here. So the positive sign keeps on rotating here. This is a very unstable condition. Carbocations are unstable, very unstable condition. Benzene is supposed to be electron rich, but here you can see how the positive sign makes the benzene ring very unstable. This situation will not last for long, and then very soon we will go to step 3. What is the step 3? Yes, abstraction of proton. When proton is abstracted, you will see how benzene ring 6 pi electrons are restored. Abstraction of proton. Let's see. This was the unstable carbocation that was formed. Everywhere positive, and here was our NO2 and here was H. Okay, now what would happen? Your base is there. Which was the base? Do you remember? The conjugate base, HSO4 minus, right? Okay, now what would happen? This electron pair, it would come back to the benzene ring system and H would go here, and now we get nitrobenzene with acid that comes back, right? So we get nitrobenzene like this. Dear students, electrophilic aromatic substitution reaction example that we have studied is nitration of benzene. There are other examples of electrophilic aromatic substitution reaction being bromination, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. If you like the video, do subscribe for it. Thank you.